Hi everyone. So today I'll be going over how to index out the diagonals of an array, both the major and minor diagonals. And this should help you on the Hackerman homework problem. So here I have three different sized arrays listed. One is a 5 by 7, the other is a 5 by 3, and then a 4 by 2 array, right? And in all of these, notice that I have just the indices listed. So these are not actual values in the array, but note that I'm just going to refer to them as indices. So what we're going to be doing is we're going to try to find what the indices are of the diagonals, and you can use that to try to index out the diagonals from your MATLAB array. So we'll begin by actually finding these diagonals, so highlighting them. So in my first array, I have 1, 7, 13, 19, 25. The second array, I have 1, 7, 13. And then the last array, I have 1 and 6. You write that out. And then 1 and 6. Right? So our goal will be to use we want to be able to use the colon operator to make these vectors because these vectors are the indices of the diagonal, right? So once we make this vector, we can then index out the diagonal. So when we use the colon operator, we always have a value that we start with, step with, right? It goes start, step, and then the final. So let's start off with the first one. And notice for this specific case, I start with the index 1, right? I end with the index 25. And notice that I'm stepping by 6 every time when we go between these. So I step with 6. Looking at this case, notice we start with 1 again, we step with 6, then we end at 13. Let's look at this last case. We start with 1, we end at 6, and notice that we're stepping by 5. So we have this, but now we want this to apply for a general m by n case. So in order to be able to do that, no, take a look at this. When we had 5 rows, notice how we stepped by 6, right, in both of these cases, but when we had 4 rows, we stepped by 5. And the reason we step by 6 is because if you count the number of extra rows, the number of rows that you have, and you add 1 to it because we start with index 1. So you can say in general, for an m by n array, you will always do something along the lines of you start at 1, you step by m plus 1. Okay? So we have these two. We have the start and the step conditions to find the major diagonal of an m by n array. So now comes the tricky part, and that is where do we stop? So in this case, if you notice, we stopped at 25. In this case, we stopped at 13. In this case, we stopped at 6. So it does not seem like there's any sort of reasoning to this. But take a look at this. Whenever we have an m by n array, we can break it down into two cases, right? So we have case 1, where we have the first case actually, where m is less than n, or we have more columns than rows. So when we have more columns than rows, notice how the diagonal will always stop after column 5. So I can keep as so if I have in this example, if I have 5 rows, I can keep adding columns to this. So maybe I can add like 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, right? Doesn't matter. It will always stop at the last, it'll always stop after 5 columns, which is the number of rows. It'll always stop at the number of columns, which is the number of rows. So if it always stops after 5 columns, notice how we will always stop at this value. The index of that will be m squared. So in this case, we have 5 rows. So the index at the value that we stop will be 5 squared. However, know that we have, so here's case 1. We also have a second case, though, where the number of columns, m, is greater than n, or we have more rows than columns. So in both of these cases, so this is the case for that too, notice that we will always stop. So here we stop at 13 because we have three columns here. So we will stop after 3 rows. However, if we added another column to this, so 16, 17, right, then we would also include this in the diagonal, and we stop after 4 rows. But essentially, when we do it in this case, notice how we can index until the end of this array. So if I do, for example, for this specific case, if I do 1 to 6 to 15, we still output 1, 7, 13. So we would index till the end because we can keep indexing by 6 to the end and know that we will never reach the next one. But if we tried the end scenario with the first array, we index by 6, we would get to 31, we would get to 37, and those are not in the diagonal, so we have to stop the first one at 25. But in this case, we can do the intuitive reasoning where we just index by 6 until we get to the end. So even if we had a fourth column, if you notice here, we would index by 6 until, if we did, for example, 1 to 6 to 20, we would get out 1, 7, 13, 19, just like we want to do. And that's the same here, right? So here I can index from 1 to 6 to 8, which is the last index, and we get out 1 and 6, and that's exactly what our major diagonal is. So in case 2, we have, so the last index of any array will always be m times n, right? So look at this 5 by 3 array. 5 times 3 is 15, because that's going to be the 15th element. It's going to be m times n. Here we have a 4 by 2 array. Last element is going to be 4 times 2, m times n. So here we have, so as we said, m times n for case 2. So now we have 2 cases and we haven't learned conditionals yet. So how do we figure out which case to use? That's where the hint comes in that we were talking about, which is to try to use the minimum function. So think about it this way. Let's say we have less columns than the number of rows, right? In that case, m times n, let's drop m times n, will be less than m squared if we have less columns than the number of rows. So here, 5 times 3 is less than 25. So where m is greater than n. But we also have this other case where we have the first case, right, where we have 7 columns and 5 rows. In that case, m times n is 35, and that is greater than m squared, right? The last index is going to be greater than m squared. So we have that case where we have m times n is greater than m squared, where m is less than n. And we want to pick the one where, and if m is greater than n, we want to pick m times n. If m is less than n, we want to pick m squared. Notice that when you compare the two of them, we always want to pick the one that is the smaller one. So we want to pick the minimum of m squared and m times n, and that will take care of both of the cases where m is greater than n and m is less than n. So we can actually index this to the minimum of m times n. There we have the first index. That's how you would index out the major diagonal. To index out the minor diagonal, we will use a similar reasoning. So notice that the minor diagonal in this case would be 31, 27, 23, 19, 15. In this case, it's just 11, 7, and 3. And I'll just do the first 2 cases for this. if we use the colon operator, right, we go from 31 to -4 to 15. Here we go from 11 to -4 to 3, right? So what we step by here is, notice how we step by -4. In this case, if I find the minor diagonal, we step by -3. And remember, again, this had 4 rows, this had 5. Notice that we will always step by the number negative times the number of rows plus 1. If you want to intuitively see this, notice that we just go minus 1, 2, 3, and we count the 1. We just subtract 4 to get to the previous one. 1, 2, 3, 4. Right? So that's what we would step by. So after we step, what we can do is we need to figure out what we start at and what we end at. So let's first try to figure out what we're going to start at. So the starting index will be, remember from before, we said that the last index of this array is m times n. This is m times n. This is m times n. So here, to get from the last index to that, we subtract 4. We do the same thing here, right? With 5 rows, we subtract 4. If we had 4 rows, we subtract 3. So notice how we can say the last, so the first, in this case, is 35 minus 4. First is 15 minus 4. So notice how we can take that and say, for example, we can do something like 35 minus, so yeah, we have that, right? So for a general case, we would start with m times n, that's the last index, and we can subtract the number of rows minus 1. Notice how we do 5 minus 1 is 4, and we subtract 4 because we just do minus 1. Here we subtract 3 because that's 4 minus 1. So this is your start. We already said that we step by negative m plus 1. That's how we step by. Now we get to the stopping index, and this is where it gets hard. But just like before, we use the same logic as before. So if we have more columns than the number of rows, notice how we only keep going until we hit the last column, but really the number of columns we go by until we hit the last row, sorry. But really the number of columns we go by is just the number of rows we have. So we really just ignore these 2 columns to the left if we have more columns than rows. But in this case, if we have less columns than rows, we go all the way to the end. So for the case where we have n is less than m, we will stop. We can say we stop at the index 1, because notice how we can go from 11, we step by negative 4, and if we stop at 1, we still get 11, 7, 3. And right, we don't do any more than that because we stop at 1. So we have case 1 where the stopping value will always, case 1, be 1 when the number of columns is less than the number of rows. However, we have another case, which is, the first one where we can't index until 1 because we want to stop at 15. Right? If we keep indexing this, we go to 11, 7. Those are not in the diagonal anymore. So here, the best way to think about this is we want to stop at the value after 5 columns have finished. So here, if we have, notice how we stop at column 3. And that is because we have 2 columns right here and 5 rows. So when we have 7 columns and 5 rows, we end up with 2 extra columns to the left. Now, if we had 8 columns and 5 rows, we would end up with 3 extra columns to the left. So in that regard, we could do an analysis like this. To try to get the indice of that value, let's say we have n columns, right? If we do n minus m, we find the number of columns that are left over to the left that we really don't want to touch. So in this case, this is 7 minus 5. After we do that, notice that the last column that we're going to pull out of for this diagonal will just be n minus m plus 1. So if we have 2 columns left over, the last column we pull out of will be column 3. Now if we had 3 columns left over, because it's an 8 by 5, so let's say we had another column right here of value, right? That's an extra column because this is an 8 by 5. We still really only want to pull out of the 5 columns on the right, so we would pull out of column 4 because we have 3 extra and we have 4. So that's why we get n minus m plus 1. And remember how we can say that any of these last indices will just be the number of rows times that specific column. So this is in column 2. This is array has 5 rows, so we can do 5 times 2 is 10. This is in column 3. 5 times 3 is 15. This will generally be true. So here if we have 5 rows and column 2, 5 times 2 is 10. That's how we can get the indice of the last element of every column. So to get the indice of the last element of the column we want to stop at, we can do n minus m plus 1, right? And then you can do that. And finally, I can multiply by the number of rows to get the last indice of where I want to stop at. So again, for this case, what this is doing is we're taking 5 rows. Let me change color. We are taking 5 rows and multiplying it by this column number. And we find this column number by taking the number of total columns minus the number of rows, which will isolate essentially this box right here. We add 1 to it to find this column number, and when we multiply the column number by the total number of rows, we can get this index. So we get this becomes case 2. So when we finally try to do this, we can do something along the lines of we start, again, remember that's a start value, at m times n minus m plus 1. That's essentially this right there. We step by negative m plus 1. And we end at here. So before we use the minimum function, this time we'll use the max. This is not as intuitive as the minimum function, and we'll do the max. And remember, case 1 was we stop at 1. Case 2 is we stop at m times n minus m plus 1. So in case 2, we use the max because here, notice how we don't want to go until 1, right? We want it to stop at 15. So the max of 1 and 15, we want it to be 15. But in this case, if we have less columns than the number of rows, and you plug in n equals 3 and m equals 5 into this equation, we'll actually get a negative number. When you take the max of 1 and this negative number, we get 1. So we know exactly we want to use the case of 1 if we have less columns than the number of rows. I encourage you to try this out just to make sure you understand why we take the max. So here is the way we can index out, get the indices of everything in the minor diagonal. And then remember up here is the way we can get all the indices of everything in the major diagonal. That's all for this video. Thanks.